Hello, so today we are going to do this problem, which is part of Leetcode Daily Challenge. All nodes distance k in binary tree. So basically we have the root of a binary tree, and we have a value target node that is called target, and we get an integer k. And what we want to do is return an array of the values of all the nodes that have a distance k from the target node. So we want all the nodes that have a distance k. And we can return the answer in any order. So if you take a look here at the first example, the target node is 5, so it's this node. And we want to get the values of all the nodes that are distance 2 from that node. So that would be this one, right? So here distance 2, and then the second one would be this one, distance 2 as well. And then this one, distance 2. So you can see even the parents count with this distance calculation. So that tells you over there that we can't just do a DFS on the tree. We'd have to do something else. So that's the idea. Now, one thing here is that the values of the nodes are unique. Okay, and so let's see how we can tackle this. Okay, so how do we tackle this? So looking at this here, we said that we definitely need to know the parents. Okay, so we need to be able to access the parents so that we can calculate the distances. Okay, so that tells you already that we need to try to create a graph out of this tree, because just having a tree, we can't access the parent unless like we add the parent to the nodes. But that would be the second solution. But for now, for the first solution, we can just create a graph out of these. What do I mean by a graph? Basically, we can mark the children as neighbors of the node, and the parent as the neighbor of the node. What do I mean by that? So for example, let's take this relationship. So that means for 5 there is a neighbor 2, and then that means for 2 there is a neighbor 5. And directed graph, that's what we'll do here. And then with the parent we'll do similar thing. So 5 neighbor is 3, and for 3 neighbor we have a neighbor 5. And we can do this with DFS. We can create the graph with DFS, because for 3, for example, we'll just say, okay, 3 has a neighbor of 5 and 5 has a neighbor of 3, and then we will recursively call DFS for 5, and then we'll create also for 5, we'll say 5 has a neighbor of 2 and 2 has a neighbor of 5, and then we'll keep doing this using DFS. Now, once we have the graph, it should be easy, because we can just do DFS again to find the nodes that are distance k. How do we do that? Well, we can just have a DFS that gets the remaining distance, right, and has the node where we are at, and each time we visit a node in a path, we just subtract 1 from the distance. And when this distance reaches 0, that means we found a node that has distance k. K is initially at the distance is initially at k, and every time we call on it, for example, let's take a look at this one, at this 5 here. So what will happen is we'll call it recursively. So first we'll call it on 5, and so when we call 2, because it's a neighbor according to our graph, now the distance that we pass, k was first at 2, now the distance is 1, and then we'll recursively call for 2 at 4, and now the distance is 0, so we will say 4 is part of the values that we want to return. And then again with the DFS, we'll go back, we will call it from 2, we'll call 7, and 7, the distance becomes 0, so we'll add 7 as well. Okay, and then similarly for 5, right, here the distance is 2 initially, we'll call it for 6, it's 1, that's not part of the values. And then we'll call it on 3, because remember the graph says that 5 has a neighbor 3, so we'll call it on 3. Now distance is 1, then we'll call 1, distance is 0, and we'll add this to the values. Okay, and those are the only values we need to return for this graph. So that's sort of the idea here. So create a graph first using DFS, and then do another DFS pass using that graph to find the nodes that are distance k. So that's one way to do it. The second way to do this is to just, for each node, okay, we don't have the parent, so just mark the parent, okay? And then, so we just do a DFS pass to mark the parent of a node. This can be easily done by using a DFS and passing for the DFS the node and the parent. Okay, and then once we do this, we'll have for all the nodes their parent. Then we can do, for example, a BFS pass. It's easier with BFS, where each time we traverse both the children and the parent, and then we find the one that is a distance. When the distance is equal to k, we add to the values, right? BFS, well, you can just add the node and add the current distance, okay? And so, for example, when we start at 5, we'll add 3 with a distance of 1. We'll add 6 with distance of 1. We'll add 2 with distance of 1. Okay? And then when we do the second pass for the neighbors of 2, we'll add 7 with the distance of 2, because we do 1 plus 1. We add 1 each time for the distance of 2. And now we'll find the distance is 2 here, which is equal to k. And so we'll add these to our values, 7 and 4. And then once we do BFS for 3 as well, then we will have the neighbor is 1. So 1 has a distance of 2. So same thing, we'll add also 1 to the list of values in our BFS. Okay, so that's the second way of doing it, is to actually add parent to the node and then do a BFS pass. Okay, so let's see both solutions and see what it looks like. Okay, so let's do the first solution, which is creating a graph using DFS. So first we need our function to create a graph, right? So that would be something like this. And then we just do our DFS. So our base case is when the node is, when we are done, we just return. And now we just go through the children for each node. So for each node has left child and right child. And we, of course, also need to create our graph data structure, which is just going to be a map. But in Python, we'll just use as default value list. And so here we'll do if child, then we want to create, so we don't want to add it for a nil child. So if something doesn't have a left or a right child, we don't want to add it to it. So the node is going to be have as a neighbor the child, but also the child is going to have as a neighbor the node. This is basically to connect the parents to the nodes. So this is actually node, okay? And then we will recurse on this child node, right? So that we can go to the next nodes, okay? And then now that we have our graph, we can just call create a graph initial on the root node, and now we should have our graph. And then now we want the values, so let's have a DFS for that. Let's call it DFS for distance k, and let's define that function here. Okay, and this function gets both the node and the remaining distance, right? Okay, and initially we want to call it on the target node, right? Because that's where we want the distance from the target. And by the way, target is a tree node. It's not a value, it's the actual reference to the node, so we can pass it. And then initially the distance, remaining distance is k. But we want also some list to store the values that we want to add, the values that are distance k from target. So that's what we return at the end. But we also, for DFS, we want a visited set so that we don't visit a node multiple times. So now let's define our DFS. So DFS base case, of course, is when the node is similar to here, when we are done traversing a path, so we just return. Okay. And then we want to check if the remaining distance is 0. That means this node is part of the values that are distance k, is part of the, because it's a valid node, it's not empty, and the distance is k because the distance, remaining distance reaches 0, it was initially k. So here that means we want to add it to the values. So we're going to add the value of the node, not the node reference. And here we can return. And now we'll visit the neighbors for the node, okay? But we want to check if the neighbor is not in visited, okay? So in Python, we can just check that it's not in the set, but we also want to add the visited nodes in the set, okay? And then here, if it's not the case, then we can call our DFS function on the neighbor. And for remaining distance, because we just visited one, we can subtract one, okay? And that should be it pretty much. So let's run this. Looks like, yeah, this should be append. And looks good. Let's submit. And that passes, okay? Now, in terms of time complexity for this solution, if we go function by function, so for create graph, if we say that n is the number of nodes in the tree, so n is basically number of nodes, then this function here is going to be O of n, because at most we will visit the nodes in the tree. And then here as well, it's going to be O(n) because at most we will visit all the nodes of the tree, because we also have a visited set that prevents visiting the same node twice. Okay, so time complexity is going to be O(n). Now, in terms of space complexity here, we are using this graph data structure that will contain at most the number of nodes. So again, O(n). And this list of values also is going to be, and visited set are going to be at most the number of nodes. So overall, it's going to be also O(n) space. So that's time and space complexity. Okay, so the other way of doing it, where we annotate the nodes with the parent. So what we do is we just do a DFS first to add the parent to the node. So basically for each node, we want to attach a reference to a parent, okay, to its parent. So initially we start with root. The root doesn't have any parent, and so we call it on it. And then here we need the base case. And then we attach to the node the parent, and then we recursively call it on the left and right side. Then we create a DQ for our tree, for our BFS. And of course we need a visited set, and we need the list of values that we return at the end. So these are the values that are distance k. And then we start our BFS with the target node. Initially the distance is 0. And then each time we pop from the front, we check if the distance reached k. If it did, then that means we have a value that we need to return. So we add it to our list of values. And then here we go through both the children, so left and right child, and then the node parent. Okay, that's because we need to include the node parent in the distance. And then we check if the node is not visited yet and exists. If that neighbor exists and not visited yet, then we add it to the queue so that it can be processed later. And the distance we incremented by 1 because we just traversed an edge. And that's pretty much it, right? So pretty similar solution, just instead of using a graph, we just attach a parent link. Now, in terms of time complexity, this function is going to go through at most the number of nodes, right? So it's going to be O(n). And then the BFS as well is going to be O(n) because at most we'll visit the nodes, all the nodes of the tree because of this visited set. So it's going to be O(n) time overall. In terms of space, we are using this queue, which is going to contain at most n nodes. So similarly for visited set and values. So again, O(n) space here. Yeah, so that's pretty much it for this solution. Please like and subscribe, and see you on the next one. Bye.